Aircraft's wheel tire cornering force. What is it? Why is it an important knowledge? Well, if you never heard about it, don't worry, because that isn't an EASA required knowledge for professional pilots. However, in my opinion, having a good understanding of this topic will greatly improve the pilot's ability to understand and control his aircraft on strong crosswind landing, on landing on contaminated runways, and taxiing on contaminated surfaces. Well, if you want to dig into the detail of the aircraft wheel tire cornering force, follow me into the pilot lounge. Ladies and gentlemen, welcome to the Pilot Lounge. Thank you for your attention today, and today we're talking about the Tyre Cornering Force. First of all, a little bit of legal disclaimer and legal notice. This channel, at the moment I'm recording, doesn't have any financial interest. And I'm sorry for the fact that you get advertising, but unfortunately I can't really control this. That is a YouTube function. And there was a plan to make this a profitable project with people working in it, but unfortunately this project failed. There wasn't enough interest in these specific technical contents. So this video remains really specific for professional pilots. If you're not a professional pilot, most likely you're not interested in what I'm saying, and maybe you won't even understand what I'm saying. So my recommendation is that it's a very little audience, I reckon, and plus my videos are very long. This is not the format ideal for YouTube. We're talking of courses rather than anything else. Courses are normally lasted for entire days, if not entire morning or something like that. Now, for the legal part, it's worth saying that as a disclaimer, I shall remind you that at the end of the day you are looking at a YouTube video, and as such, obviously you should not use your day-to-day operation. You should not act based on what you see on a YouTube video. So obviously your manufacturer, your company SOPs always take precedence. What we're doing here, in few words, we are giving you a little bit of food for thoughts. I give you a little bit of hints, a little bit of information. It is your responsibility to grab this information, to build up understanding of the topic and implement the regulation and your company procedures properly. As a disclaimer, I therefore have to say that it's just an informational video, very often containing information that are also incomplete. So what I'm saying cannot be used for any legal purpose, like, for example, justifying any action or demonstrating that that is the common pilot behavior or habit of doing whatever kind of procedure. This is, in few words, a way that I use to remain in contact with my former students, but sometimes they still look at my video, and eventually, even after years of completing their line training, completing their initial ATPL training, sometimes they still remain somehow for a few minutes the student. What we're looking today is Cornering Force. It's a course that normally would take an entire morning, and this video is a bit shorter than an entire morning. What is interesting in that this course, as I said, is not part of the ATPL required knowledge, and when something is not part of the ATPL required knowledge, it gets withdrawn. I found, however, this knowledge extremely important in my career, and at the end of this video I will tell you why. There's going to be a little example on this, and for this reason it's one of the things that I say, yes, I want to discuss this with my audience. I think though is not a required knowledge. I think it's really interesting. Let's go with the titles, and then unfortunately we have to start with a bit of math and physics. Please bear with me during this phase of the math and physics, because they are the fundamental part, that are the most important part to understand the rest of the discussion. it rolls by itself. It goes without saying, obviously. However, if I put it on the side, obviously it won't move. I can push it, but it stops every time. And you will say, well, this is logical. Now, at this point, I want to repeat this experiment by increasing the weight of my bag, and I guess you will understand, obviously, what will happen when the object is heavier, but let's try it anyway. This is heavy. It won't pass the Ryanair gate without a fine. Now, on the wheels, there's nothing changing. The bag still rolled by itself. When I put it on the side, again, it doesn't want to move. But let's get some numbers. I have measured the force I have to apply in order to produce movement. And you see that when the bag is on the wheels, in order to produce something that it appears to be the same acceleration, the same movement, I have to apply more than twice as much effort. Because, as we previously would say, that is one of the fundamental Newton's law. The force equals mass times acceleration. So if I want to have a similar acceleration, by increasing the mass, I have to increase the force that is applied to the body. When the bag is inflated, in order to obtain the sliding, I want to make you notice that light bags start to move. I have applied a force of approximately 3 kilograms. Once instead, on the heavy bag, when I applied a stronger force of 4 kilograms, the bag still didn't move. To obtain the movement of the heavier bag, I had to apply a force of approximately twice as much. It was 8 kilograms when the bag started moving. Now, in order to maintain the state of motion of this bag, look at what happened. If I would release the bag, of course it would stop immediately. So in order to maintain a state of motion, you see that on the light bag, on the empty bag, I was applying something like 500 grams of force, while on the heavy bag I was applying a force in the range of 5.3 kilograms. So we can say that still I do require a force to produce the movement, but this force is not exactly the same of the force that I required in order to start the movement of the bag. So the facts are exactly this. I need a higher force to start movement, and I need a force, a continued force, lighter, to maintain the movement of the sliding object. And the equation of the frictional force is frictional force equal the normal force multiplied by the coefficient of friction. To understand this phenomena, we have to discuss the inclined plane. If I have a surface with a small slope and I put my bag on it, my bag will not fall down, you would say. But if I tell you if the slope is very high, will the bag fall down? You would say yes, obviously it will. Now, what are the physical forces that decide whether this bag should fall down or not? Well, when I have an object, my bag, resting on the surface, I have only the force of gravity applied to this object. But this force of gravity can be divided into components, one which is parallel to the slope and the other which is 90 degrees with the slope. Obviously, if the one which is 90 degrees is too big, because the object is too heavy, well, the surface will break down and the object, my bag, will fall down underneath the inclined plane. But if the surface of the inclined plane is hard enough to support the weight of my bag, or at least that component of the weight of my bag, well, then there will be a normal force. The normal force is equal and opposite to the component of the gravitational force which is pushing my bag towards the center of the earth. The remaining part of the weight of the bag, which is parallel to the inclined plane, is the force that will produce the movement of the bag. But however, my bag eventually will not move because of frictional forces. This frictional force is nothing else than a force which is connected to the normal force. So existence of frictional force is only conditional to the existence of the normal force. And the equation that regulates this connection is that the frictional force is equal to the normal force multiplied by the coefficient of friction. Ladies and gentlemen, we are talking of your friends. We are talking of the braking action. Coefficient of friction is the braking action. Now, if the coefficient of friction isn't strong enough, it results that the frictional force is not enough. Of course, the frictional force will only be equal and opposed to the gravitational component of the force that wants to produce the sliding down of the bag. Meaning that if this gravitational force is little, the frictional force is little. But if this force starts increasing, or if this frictional force is smaller because the coefficient of friction is too small, well, then it turns out the frictional force is too small as compared to the component of the weight of the bag, and the bag will start sliding down. But here comes the second trick, ladies and gentlemen. Something that pilots never get told, and it's the coefficient of friction is not a fixed number. Well, we kind of know it because of course we get given braking action, but we'll see that this number is highly variable, not only measured and constantly valid. For this reason, when the object is moving, in the case of rubber against tarmac, the coefficient of friction is typically changed. So for high school point of view, what student will be given is a coefficient of friction for static friction and a coefficient of friction for dynamic friction. So once this bag is sliding downhill, now the coefficient of friction is dynamic. And the dynamic coefficient of friction between rubber and tarmac is typically between 40 and 60% less than the static coefficient of friction. Meaning that as soon as my bag starts going down the slope, the coefficient of friction will reduce dramatically, meaning that the frictional forces will reduce dramatically. And here we got what we have on my video. If we look back at the numbers I have recorded, you will see that once the bag was empty, the force that was required to start the movement was in the range of 3 kilograms to start the sliding, and I just needed something like 500 grams to keep it sliding. When the bag was full of books, I needed up to 8 kilograms to start the motion of the bag, and I still needed 3.5 kilograms to keep the motion. Now, of course, this is not really a scientific way of doing a measurement, I know it very well, but basically I was trying to give some kind of number to a physical phenomena that we know very well. We've all been displacing a very heavy bag and a very light bag. We all been trying to move a piece of furniture knowing that if you start moving it, once you start moving, then it's easier to keep it moving, you know. But bear with me one more second because I want to do a last test. In this example, I have locked the wheels of my bag, but not in the way that they cannot spin. They're free to spin, but what happens, they can't twist, they can't turn on themselves. What I observe in this case is that if I try to make the bag slide on the side of the wheel, not on its longitudinal direction, the effort that I need to make the bag move is similar to the effort that I need when the bag is on its leg. And to keep the motion, again, I need to apply a force which is similar to the one that I need when the bag is on this leg. So, in few words here, I'm demonstrating something which, again, it's absolutely obvious. I have a wheel, and this wheel is designed to work in its longitudinal way, on this direction, okay? But if I take this wheel and try to use it in this directional, obvious, this is a sliding object. If you think about it, a wheel which is sliding on this way, rather than rolling, is nothing different than the leg of a piece of furniture which is being pushed in one direction or the other. Now, the piece of furniture will always have dynamic friction coefficient, and the wheel sliding on the side will have dynamic friction of coefficient. Now, what is interesting to note that instead, if the wheel is rolling properly, every single point of the wheel remain in contact with the surface in a static way. So the wheel, the surface of the rubber, remain in static contact with the tarmac, meaning that when the wheel is used as it should, what happens is that there is static friction between the wheel and the surface. And I just told you that the static friction is significantly higher the coefficient of static friction significantly higher than the coefficient of dynamic friction. And this is the key element of this course, the Tyre Cornering Force. What we are looking at is not particularly the forces which are applied in a longitudinal way with the wheel. We will discuss on this indeed. But what we are particularly interested today is the side forces, the cornering force, the side force which are applied to the tire and the effect of these tires. Having discussed the frictional forces and the difference between static and kinetic frictional forces, and indeed after a good coffee, we can now, or I can now tell you a bit more in detail, a bit more of truth about these frictional forces, because I've been lying to you. In some cases, the static and kinetic frictional force could even be the same number. So, or I should say the static and kinetic frictional coefficient, but not the frictional forces. The formula remains the same. The frictional forces equal the normal force multiplied the coefficient of friction. And the coefficient of friction could be the same, but the number is not the same. Now the thing is getting really confusing. I've been looking on tire manufacturers, and on the website I found that no aircraft tire manufacturer is publishing tables for frictional forces, so I couldn't find any relevant information. Actually, on the internet, the most relevant study that can be found, and I would say the most interesting, is an NASA study of frictional forces on aircraft tire, which however was done in 1977, so a few years ago. In this study, we can see that there were frictional forces measured for several types of tire on several surfaces, and this one, as pilot, we know very well, the braking action is changing noticeably if the runway is wet, contaminated, dry, and so on. So that's not the news. But what is interesting is that it was found that frictional forces was changing with speed. So at 100 knot, I got less frictional forces than a low speed, and it was changing on tire pressure, temperature, a high number of environmental factors, not only the type of tire and tarmac. So it was also found, there was a measurement basically for the static frictional force, so the rolling tire, the kinetic frictional force for the block tire, and it was also measured the frictional force in case of cornering, so where the tire has an angle with the motion of the vehicle, and this will be the case when the vehicle is turning. So instead of the tire rolling this way, the tire is rolling, but is rolling with an angle, okay, moving in this direction while rolling. And they also measured the sideway frictional forces. Now what was found is that yes, in some cases the frictional force for a block tire is the same of a rolling tire. The frictional forces for cornering tires are typically a bit less, so this means that the tire accepts, I would say, less prone to transmit sideways efforts, but this one I would say again is pretty obvious. The tire is designed to work in the longitudinal direction, not on the side direction, so this one is not a big change. And the final conclusion is that the frictional coefficient, the coefficient of friction, is an extremely variable number. In fact, when we talk about braking action, actually we talk about a runway assessment, a set of friction coefficient, not just one friction coefficient. To understand why, anyway, there is a massive difference between a kinetic friction coefficient and a static friction coefficient, however, we have to define what is the traction circle. If we take a tire seen from above, the tire is applying an effort on the runway, and the runway is applying an effort to the aircraft which corresponds to what the pilot wanted. For example, decelerating, if I want to brake, well, the energy of the aircraft is transferred to the tarmac, and the tarmac is transferring energy to the aircraft by decelerating the aircraft, okay? The tire seen from above, we know that the tire force has a limit. If I exceed the maximum limit, the frictional force will be too small, and then the tire starts skidding. So I can define as the traction circle the area where the combination of cornering force and longitudinal force will produce a tire force which falls within an acceptable frictional force. We, as pilot, need to define those two forces. Why? Because the longitudinal force is the braking of the wheel. Okay, the cornering force could be on the nose wheel, the steering. So I'm steering the wheel, producing intentionally a cornering force in order to produce the aircraft to turn. Or it could be simply that I'm landing on crosswind. Once I am on the ground, well, the wheel will have to sustain some side forces because the wind is pushing the aircraft downwind of the runway. I will counteract these with the rudder, but the rudder will actually use the main gear as a pivot point in order to keep the aircraft aligned with the runway. So for this reason, the wind is going to be pushing, producing a cornering force. Now, what happens if the tire force is too large? As I just said, what happens if my bag is on a slope which is too high? Well, it starts sliding. So we move from static frictional coefficient to dynamic or kinetic frictional coefficient, and the wheel starts skidding. Now, the big difference of a skidding wheel is that a wheel that spins can produce a force longitudinally and sideways. The sideways, the cornering force, can produce, for example, on a car, on a vehicle, can produce the turn. So on the nose wheel steering can produce the aircraft to turn. If you take the leg of a table like this and you start sliding it, all that the kinetic friction coefficient can produce is a frictional force which is opposite to the direction of the movement. With a sliding object, you can't control the direction of the object using the leg of a table. The leg of a table, once you push the table, will not direct the table left or right if the floor is horizontal, of course. So, in few words, once you have a friction of coefficients, which is the dynamic one, the wheel is skidding, and if you think about it, there is no difference between a skidding wheel and the leg of a table. And that's why on my bag I then did the test using the wheel at 90 degrees. Again, there is no difference. If the wheel is skidding in whatever direction, is exactly the same of the leg of a table skidding. So two objects, no matter their shape, they still skid the very same way, meaning that the force that is produced by the tarmac on the wheel is just opposite to the direction of the movement of the vehicle. Meaning that, for example, this is why the ABS in the automotive was a great invention, because what happened? I saw an obstacle in front of me, I started braking and I blocked the wheel. If I block my wheel, what happens is that the wheel starts skidding and the vehicle keep going straight. Keep decelerating with a frictional force which is normal force multiplied the coefficient of kinetic friction, but we'll keep going straight. With the ABS, the wheel keeps spinning, so the friction of coefficient is slightly higher. We would say is much higher, should be double, but that is not the big difference. The big difference, where the coefficient of friction is really, really higher, is that if I start turning the wheel, now the cornering force is still present. So the coefficient of friction dramatically drops when we look at cornering forces and skidding wheels. So if the wheel is turning, then the coefficient of friction is present. In fact, in the NASA study, it wasn't even measured. There wasn't even a table for cornering forces of skidding wheel. The cornering force were only measured on rolling wheels. If the wheel is skidding, the cornering force is zero. Meaning that in the automotive, if I see an obstacle in front of me and I hard brake and the ABS release the brakes, allowing the tire to spin, what will happen is that if I try to avoid the obstacle by turning sideways, the cornering force will still allow me to direct my vehicle. So maybe I cannot stop in time, even with the ABS. But now I can still keep control of my vehicle and steer left or right. Having discussed the importance of not blocking the wheels, we now get into the aeronautical anti-skid system that, as you very well know, prevents the wheel from blocking and therefore the wheel from skidding on the ground. A skidding wheel cannot produce any cornering force and therefore cannot counteract a crosswind, causing the aircraft to skid on the side of the runway and eventually producing a sideways runway excursion, while a rolling wheel can produce cornering force and therefore keep the aircraft on the pilot's desired path. For the maneuver of landing and rejected takeoff, the importance of speed brake cannot be overemphasized. Why? If you think about it, when you're approximate to V1, you're approximate to VR. And at VR, your wings can produce enough lift to lift you off your aircraft. Yes, you say I have to increase the pitch angle, so I have to increase the angle of attack. But still, some aircraft, when light, they can lift off even with 2 or 3 degrees of pitch angle, so the rotation is very small, meaning that the wing already produces a very high amount of lift. And the friction coefficient, or anyway, the frictional force is the friction coefficient multiplied by the normal force. Now, if your wing can lift your aircraft, the normal force is already very low, even with the 3 wheels on the ground during a rejected takeoff or during landing. For this reason, the speed brake are extremely important because they discharge the weight of the aircraft on the wheels, and your braking capability is strictly connected with the weight, with the normal force. Here we have the example of a 20-ton aircraft which is decelerating with and without speed brakes, and you see that the stopping distance, if the normal force is double, the stopping distance is half of it, assuming we are applying maximum braking and of course the anti-skid is working properly. On the Boeing flight crew training manual, we're not given the weight and environmental factor of the aircraft, but Boeing shows that basically on a rejected takeoff executed at exactly V1, if we use reverse, we reduce the certified landing distance by 65 meters. If we omit the use of speed brake, we increase the landing distance by 130 meters, meaning that the speed brake are more effective than reverse in the deceleration of the aircraft, which wouldn't sound obvious, you know, because you say, okay, the reverse is a, you know, it's a forward, I mean, it's a positive thrust, it's a positive push in the stopping direction, and instead the speed brake, the speed brake just discharge the weight of the aircraft. They increase the normal forces, and increasing the normal forces give a greater efficiency of the brake, enormously greater efficiency, as we saw in the previous example of the 20-ton aircraft, where it was actually stopping in half of the distance. Okay, at this point we can start also discussing the tire elasticity and discussing this little bit piece of knowledge that you should have from your basic TPL knowledge, is that the anti-skid will actually avoid the wheel from skidding, but will actually release the brake when the spinning speed of the braking wheel is something like 90 and 80% less than the free spinning wheel. And this is something that sounds curious. You say, why should the anti-skid, you know, allow a little bit of skidding of the wheel? In reality, the anti-skid is not allowing a little bit of skidding of the wheel. It's just allowing a lower rotation by keeping a static contact patch, so the tire and the tarmac remain in static contact. Okay, but if you think about it, when you start applying a force, so when the wheel start braking, what happens is that this is the longitudinal force applied to the wheel. Okay, with this longitudinal force, the area in front of the tire start compressing because of elastic deformation, and the area behind the tire start extending. Actually, the contact patch start moving forward because all the energy of the aircraft is actually transmitted by the tire to the tarmac. This compression and elastic deformation will allow the tire to spin at a lower speed, and this spinning corresponds to the maximum elasticity capacity of the tire instead of a free spinning wheel. So this 80 or 90% less spinning speed does not correspond to the skidding of the wheel. This phenomena will occur also sideways. So basically, when the tire is applying a strong cornering force, the tire will have a deformation, will actually get in an inclined shape, and the newly arriving points that will be in contact to the tarmac, actually they're coming in straight. And only once they are in contact with the tarmac and they start transferring force, they move elastically and they move to the side. So when there is a cornering force, the tire again is allowed a little bit of skidding. If there is the tire turned by 20 degrees, for example, there is a little bit of skidding and the vehicle actually is going to turn maybe by 15, by 10 degrees. So there is a little bit of drift angle. That's what is called in automotive, okay? It's not the aircraft drift angle, but the drift angle is exactly this angle between the direction, the longitudinal direction of the tire, and the actual direction where the tire goes when there is a cornering force, and this is due to the effect of elastic deformation of the tire. In conclusion, this deformation of the tire will make normal that the anti-skid accept a lower spinning of the wheel, and that the wheel has a so-called wheel drift angle, meaning that the vehicle will turn not exactly in the longitudinal direction of the tire, but with a little bit angle as compared to the longitudinal direction of the tire. Let's get now to the heart of the matter, which is the cornering force, finally. Why is it the heart of the matter? Well, what we want on landing is the longitudinal force, is the braking force. So yes, we want braking, and we discussed the importance of speed brake indeed. But when we land on contaminated runway, when we land on strong crosswind, what happens is that we are flying with a crab angle. You very well know that we should decrab the aircraft prior landing. In some aircraft model, it is even accepted that the aircraft is decrabbed if the runway is wet or contaminated, that the aircraft is decrabbed after touchdown. Both techniques are okay, and it's totally acceptable to decrab the aircraft after touchdown. The heart of the matter here is the importance of decrabbing the aircraft promptly after touchdown, or even before touchdown. Why is this so important? Well, we say anyway, you got the anti-skid, will avoid your wheels from braking and skidding on the runway. But if I land with a crosswind, what happens is that when my wheel touches the ground and I have a crab angle, I will produce, yes, a longitudinal force for the braking, actually in this direction, but I will produce a cornering force as well. So the longitudinal deceleration that is in this direction, I want to decelerate the aircraft in the direction of the flight. But this deceleration corresponds to a longitudinal force and a cornering force. Now, the longitudinal force can be very well managed by your anti-skid system. But the cornering force, there is nothing that the anti-skid system can do about it. So if this cornering force is too high, your tire force will fall outside the traction circle. And when the tire force falls outside the traction circle, the result is that the traction circle shrinks to a smaller traction circle, where the friction coefficient is the dynamic, is the kinetic coefficient of friction. Even worse, we say the cornering force is zero in skidding objects. So if your wheel lands with a cornering force which is excessively high, what happens is that your wheel starts skidding, and there is nothing the anti-skid can do to produce braking, because the exceeding part of the tire force is not in the longitudinal direction but is in the sideway direction. And here comes the worst. If there is no friction between your tire and the tarmac, so if your tire is skidding on the tarmac, what happens is that normally we switch from controlling the aircraft about its center of gravity, because once you are in flight, of course, your flight controls your aircraft about the center of gravity. But once you touch down on the ground and the wheel is in contact positively with the ground, even with a small cornering force, but there is static friction coefficient, now when you move the rudder, what happens is that you spin the aircraft about the point of contact with the ground. So you switch from center of gravity to main tire controlling of the aircraft. If the wheel is skidding, this switching doesn't occur. So it means that as soon as you try to align the fuselage to the center line, because there is no friction, the aircraft will start skidding sideways. That's exactly what happens when you are in crosswind and you remove your wind correction angle. You start drifting downwind, okay? So as soon as you try to align your aircraft to the center of the runway, the aircraft will have tendency to drift sideways. This drift sideways, which is produced by the crosswind, could again have a too high cornering force and make it impossible for the tire to develop the grip. This again is combined with several factors, out of which the speed brake, I would say, is the main factor, because the key element on landing is that you actually move from the dynamic coefficient of friction to the static coefficient of friction, which has a higher traction circle. So you see that during the landing in strong crosswind on contaminated runway, the landing technique can change a lot in the landing distance, because if you manage to align the tires of your aircraft at exactly touchdown or prior touchdown, this will allow your tires to have exclusively longitudinal forces. This technique has to be made prior or before touchdown in order to touch the runway with the smallest possible cornering force, because if the cornering force is excessive, either I keep increasing the wind correction angle as the aircraft is on the runway and decelerate, and by increasing the wind correction angle actually increase the cornering force and I worsen the situation. The anti-skid will never apply brakes because the wheel is keeping on skidding. Either I neutralize the wind correction angle, but then I allow the aircraft to drift sideways off the runway. For this reason, it is extremely important to deploy speed brake and spoiler immediately after touchdown in order to produce the maximum normal force on the tires, and with this maximum normal force we have to attempt to gain the static coefficient of friction. We have to put our wheel in static contact with the ground, and only then the anti-skid can start applying brakes. If you ever find yourself therefore in the situation where the crab angle is too high, or you have the sensation that this cornering force is way too high because the aircraft is drifting sideways of the runway, I would say the go around is the most advisable maneuver. But I remind you that generally speaking, depending on aircraft model, the go around is never an option once the reverser is deployed. It has to be said that in all cases the reverser cannot guarantee the full stop of the aircraft. Reverser is very effective at high speed, but as the speed goes down the reverser gets less and less effective. Of course, this is not the case for a propeller aircraft, where the technique is completely different, and in a propeller aircraft actually the problem is less significant, because as the speed reduces the coefficient of friction will increase, and therefore the availability of brake and the chances to be able to regain control and brakes will increase. On jet aircrafts, most of the operator will recommend, in case of loss of control of the center line during deceleration, to reduce thrust to idle, use the rudder to regain control of the center line. Once the aircraft is again aligned with the center line, increase the reverse thrust to the desired level. I remind you that reverse thrust normally it is not recommended on any jet aircraft at low speed, but in case the runway is contaminated, you are safe to use as much as maximum reverse thrust, even if this could cause engine ingestion of FOD, but maximum reverse thrust might be used and needed even at low speed to guarantee the stopping of the aircraft. Once again, the main stopping system once you are below 80 knots remains the wheel tires. So in few words, this is the explanation of why the crosswind limits exist for wet and contaminated runway, because the more the runway is contaminated, the less cornering force is available, the less side control capability I have for the aircraft. And once again, the key element there was to understand that the anti-skid can only work on longitudinal forces, and the cornering force are exclusively left to the pilot. So it is important that you keep your aircraft aligned to the axis of the runway during the deceleration of the aircraft. The other set of wheels that require cornering force is the nose wheel steering. The nose wheel, of course, is directing the aircraft, and therefore there's no braking, no longitudinal forces. It exclusively uses cornering force to direct the aircraft. We say it is normal that there is a little bit of technically called drift angle between the longitudinal axis of the tire and the direction of the aircraft. That's a normal functioning of all wheels in all vehicles. We don't even see it. What is the complex thing of the aircraft is that having the nose wheel, which is relatively far away from the pilot, if the nose wheel starts skidding, it is not evident. Sometimes we can hear some noise. We have two wheels, so what happens is that sometimes just one of the two starts skidding, so we still maintain some kind of directional control. But overall, if both wheels are skidding from the nose wheel, what happens? The result is that the aircraft keep going straight, will not turn left or right. In that case, we can use asymmetric braking, because this time the asymmetric braking has the anti-skid, and the asymmetric braking can help us in maintaining direction of the aircraft. But again, if the runway is contaminated, the anti-skid will release the brake and will not be really effective. Most importantly is that the anti-skid could release the brake at different settings on the different pairs of wheels. So if I'm applying maximum braking with the nose wheel steering skidding, basically I will be uncertain of the actual direction of the aircraft, because maybe one set of wheel brake more than the other set of wheel on the main gear, and the aircraft will be going left or right. Unlike light propeller aircraft, on jet aircraft the elevator has very little aerodynamic capability. It is therefore not recommended to hold the nose up during the deceleration. The best technique on jet aircraft is to have a light forward pressure on the elevator in order to increase the normal force on the nose wheel and avoid having the nose wheel skidding during the landing. So as a last resort, you should use braking up to max braking, of course. Maximum braking, I'm talking of speed normally obtained during taxi, but the main way to direct your aircraft is indeed the nose wheel not skidding, using the cornering force of the nose wheel. What should you do therefore if the cornering force is excessive and the nose wheel is skidding? Is very simple. Reduce the angle of steering, so reduce the so-called drift angle of your wheel. Start aligning the wheel with the neutral position. The wheel will start spinning again. Once the wheel spins again, you regain static coefficient of friction and you can start turning again. Braking will help in increasing the normal forces on the nose wheel, because as you very well know, when you brake, you discharge more weight on the nose wheel. So combining light braking. Why light braking? Because you don't want to have the effect that I just told you of having anti-skid, making your aircraft braking asymmetrically. So you apply light brake, making constant and equal braking on the main wheel, reduce the angle of the nose wheel. This will increase the spinning of the nose wheel. By increasing the spinning of the wheel, you regain static coefficient of friction, and now you keep turning. Probably you were taxiing a bit too fast for that runway surface, so it might be a good idea to keep a light brake pressure during the entire maneuver, so that you start turning, keeping a light brake pressure, reducing the speed of the aircraft, because as I say, probably you were taxiing a bit too fast. Now, as I said in the beginning of this video, there is also a real life story to tell. This is personal experience, something that happened to me. What happened is that, as I say, this course is not regulatory requirement. In the past, when I was a student, it was rather the airline companies making specific course on their own discretion, not really on the authority requirement. So yes, I received a Runway Excursion Prevention Course. Actually, my instructor was a very old pilot that flew on the Super Constellation, so today is not there by a long time. But I very often use this example not really to explain the cornering force, but to explain what a good instructor is, because this is definitely the example of a good instructor. Okay, I received this course when I was a student pilot. I had 170 hours of flight. But after that, never had some training, some positive training on that, was just self-study. I was a newly promoted captain. I was flying with a relatively inexperienced first officer, and that day we were flying to Manchester. Now, airline pilots, they probably know that English ATC, it's very professional, it's very good, but unfortunately has the very bad reputation of writing lot of letters to your companies. And when you are a newly promoted captain, the last thing you want is a letter coming from the traffic control complaining for whatever kind of sort of problem. And I remember my briefing to the first officer was exactly this. We both low on experience. The last thing both of us wants is a letter. So we have to be really standard. We really have to pay a lot of attention to what's going on, make sure we comply with the ATC instruction. I did my briefing, and my briefing actually had a strategic decision. I was thinking to vacate Alpha Echo. This will give us a little bit longer landing distance.
Yes, and we're just 1 ton below max land weight. We must consider brake cooling.
Exactly, we will stress less the brakes, we'll have less brake cooling time, and once we are on Alpha, you'll do the after landing procedure, and then we can take a bit of time to discuss the taxi route. You know, we're a charter. I think we're gonna get a remote stance. The airport is not way too complex. But still we have to use caution with the taxi instructions, okay? So this will give us time to analyze it. What happens is that we find ourselves in final, as every day in UK it's raining, so the runway is wet, and it was soaked wet since the beginning of the day. Maybe it has been raining for the entire night, and we get in contact with tower. Unlike it is every day in UK, there is no strong headwind, so the wind was fairly light. And the towers tell us,
Uproad 29 Foxtrot, clear to land runway 23 right, vacate Bravo Delta.
Roger, clear land 23 right, will vacate Bravo Delta, approach 29 Foxtrot. Alright, this will require auto brake 3.
But what about brake cooling? We must go for a quick turnaround.
You're right, we'll better keep the brakes where they are. I think we should be okay, you know, marginally, maybe a bit of mono braking. We're gonna be okay with brake cooling.
50, 40,
wow, exit
30,
Bravo Delta is way
20,
shorter than what I expected.
retard,
Uproad 29 Foxtrot, expedite vacating and continue taxi Alpha, brake, Speedbird 5 Kilo Yankee line up and wait. Be ready for immediate.
Alright, 100 knots, my controls.
Your controls.
Oh, we're a bit fast there.
That's the next one. We're skidding.
Off the brakes. As we reach this tight turn, I start turning with my nose wheel steering, and guess what? The nose wheel starts skidding. Got really caught by surprise. Of course, we slam on the brake, but this actually worsened the situation because of the anti-skid problem. So mainly the aircraft kept going straight. But this is because on the specific aircraft I was flying, like it is on many major transport aircraft, what happens is that the anti-skid has a secondary program. The secondary program will actually reduce the braking on the wheel that has more friction in order to avoid the aircraft having significant yawing when one of the main gears actually has to release the brake due to skidding. Not all aircrafts have this function. Which probably means that the main gear found itself on a lot of rubber on the right gear and good quality tarmac on the left gear. And this worsened the situation. The maximum braking caused the aircraft to yaw a little bit to the left because probably the left gear was braking more. And that's where, the voice of my instructor came into my mind. And I tell you, that was really surprising how after 20 years, of having learned something, how much a good instructor can be effective. I would have never said that after such a long time, the words of my instructor would come up into my mind. I never have really recalled those words. And it was like if it was there, like if that pilot was sitting with me on the jump seat and just told me to lower the braking, center the nose wheel, and that's what I did. We released the brake. Actually, I said to the first officer to release the brake, and I centered the nose wheel, applied gentle braking, and then started steering again in order to regain control of the aircraft. That day we saw the grass of Manchester from very close, too much close. But knowing the correct technique and accessing this knowledge promptly, and thanks to a good instructor that found the way to put these words into my mind and keep it there ready to use after even 20 years that this was said, with these elements actually I saved my command. We regained aircraft control. We didn't get any letter from the ATC. Nobody ever realized whatever happened, of course. We got to the gate safely, and what could have been a very sad ending of my command career actually transformed into a very good experience. So I hope that this video, you will never need to apply what I just explained to you in this video, but I hope that maybe this information could be useful to you one day. Of course, as I said in the beginning, make sure that what I just said apply to the specific SOP of your company, apply to the specific model of your aircraft, and make sure to comply with all regulatory and instruction information. But here we discuss some of the basic knowledge, which again is not a legal requirement, but which could be useful to build up a full comprehension of the problem and sort out the situation as it did for me. So I hope you enjoyed this course. Did you like this course? Would you like actually to have an entire runway excursion prevention course? Do you think it would be useful to invest an entire day on this type of course or not? You can leave it in the comments. Runway excursion prevention course and other courses remains available from myself. You can look in the comment and the available courses that I have. Of course, these are organized with the sponsor Aviomar. And ladies and gentlemen, thank you very much for your attention today. As I said in the beginning, there's no real financial interest in the like and subscribe and so on. So if you do, I appreciate. Otherwise, I don't really mind. But thank you for your attention, and I hope to be able to come back to you with new content in the future. Thank you and goodbye.